Hello everybody and welcome back to Dynamics Lectures, Intergalactic Instruction. This is Lecture 2 of the Dynamics course. Today we're going to have a couple of guest stars on the program. We're going to be hearing from Einstein, and we're also going to be hearing from Boba Fett. Okay, let's jump right back into it here. We got the kinematics of a particle. That's what we were talking about. Dynamics. The dynamics course is eventually going to have two things to consider. One of those things is a particle, and one is a rigid body. Now, a particle is something like, hold on. A particle is a little dot. An infinitesimally small dot, massless, no mass, it's just a particle. So it's actually easier when we're just talking about a particle, how it moves, its simple equations. When we get into something different, which could be like this or whatever shape, a rigid body, it's a whole body. It has a mass. We might be describing how the body moves. We're going to need a coordinate system, X, Y, and Z. And it will get more complicated once we get into stuff like that. But for now, it's just a particle, and we'll continue on and get the basics of the dynamic equations just by talking about a particle. But prepare yourself for it to essentially become more complex when we delve into the realm of rigid bodies. Now, specifically, when we're talking about dynamics, you can expect most problems to be asking for a particle's position, a particle's velocity, or a particle's acceleration at any given time. Or it might even ask, at what time is it traveling at this speed? These are the main vocabulary words to pay attention to. Position, velocity, acceleration, and then time. Those are the key words in any dynamic equation. I put this sentence in here saying typically we expect to see acceleration because the equations of motion are a lot easier if it's just traveling at a constant velocity. That's like something you might see in middle school or something. A train is traveling at 30 miles per hour. How long does it take to go 30 miles, right? It takes an hour. There might be some YouTube stars who got famous by not knowing the answer to that question, but you guys should know it, so don't expect to see your teacher giving you anything that has to do with just velocity. You will most likely have some form of acceleration in the problem. Just to recap, in the last lecture we did talk about rectilinear being straight path. Rectilinear motion equals a straight path. Curvilinear motion equals a curved path. And we got new equations to come in this lecture. Just one, really. I pretty much gave you all the equations you're going to be using for particle kinematics of a particle in the last lecture. But I'm going to add one more, and I'm going to derive it real quick. It's a real quick, simple derivation. And I'm also going to explain Einstein's most beautiful thought. Okay. Here are the kinematic equations that we talked about last time. Now these equations have to have constant acceleration. So if you are given a problem where velocity equals a certain function, like let's just say it equals 9t squared, then acceleration is just the derivative of this, like we talked about last time. It's going to be the derivative of that. It equals dv dt. So therefore, we can expect that to be 18t. Is this constant acceleration? No. 18t. It varies with time. Time is a variable. So that is not constant acceleration. Therefore, we cannot use any of these equations if acceleration is not constant. But if you do see in the problem that acceleration is constant, look to these equations and they will get you through it. We went over them last time, so I'm not going to talk too much about them again. Now, I also specified last time that we have position, velocity, and acceleration. Velocity equals dx dt, and acceleration equals dv dt. So what if we solve both of these equations for dt? Well, let's go to the blue color. dt for this one will be, move the dt over there, it's going to be dx divided by v. Red for here. dt for this one equals dv divided by a for acceleration. So now we can set these two equal to each other. dv Alright, and I'll just keep it in blue. Let me scroll down a little bit, give myself some room here. And to wrap it up, let's move the v over there. V dv equals a dx. So this is also an equation that we might see or might need to utilize when we are solving problems for dynamics. V dv equals a dx. Alrighty then, so let's welcome out today's guest star of the lecture. One of today's guest stars of the lecture. We got a couple people coming on today. The first one is Albert Einstein. And we're going to talk about the most beautiful thought that Albert Einstein ever thought. He was working one day in his patent office in Germany, and it's been said that he saw a painter across the street painting the building, and the painter abruptly fell off his ladder or whatever he had. Let's make him hold a little paintbrush here. And he plummeted towards the ground to meet certain death. And this provoked Albert Einstein to have the most beautiful thought he ever had. Now, this is, we're not sure if this painter really existed or not. No one really knows. But let's just say for the sake of this most beautiful thought that he did exist. While this painter was falling towards the ground, hurtling towards certain death, Albert Einstein realized that this painter no longer experiences the feeling of gravity. Now, we are on planet Earth, so he would feel some wind resistance, but he no longer experiences the feeling of gravity. Gravity in metric components equals 9.81 meters per second squared. And that is the acceleration at which we are forced to the ground every day. And this painter, as he fell, no longer felt that. And that is the beginning of Einstein's most beautiful thought. A way that I've heard it worded differently that got me to really understand it was, let's put this guy, let's bring this painter back to life and put him in an elevator. And put that elevator in outer space. And then let's accelerate this elevator in outer space directly upward. And let's not just accelerate it at any speed, let's accelerate it at 9.81 meters per second squared. The person in this elevator will feel the exact same sensation that we feel on Earth, the exact same feeling of gravity. Just a random person in a random elevator accelerating at 9.81 meters per second squared in the abyss, in outer space. And he will get the same sensation as gravity. And that is the most beautiful thought that Einstein ever experienced. Okay, now let's jump into some problems. Okay, let's jump into a problem real quick. We got Boba Fett jumping into the equation here. Boba Fett's jetpack launches him into the air at a velocity. This is a velocity, important information, of 75 meters per second. When he reaches 40 meters of the ground, I should say off the ground there, let me fix that. Off the ground, he shuts off the jetpack. Okay. Gravity on this planet is the same as Earth. It's 9.81 meters per second squared. What is the maximum height that Boba Fett will reach? Okay, so let's draw this out. What do we know? One thing, we know that initial velocity equals 75 meters per second. We know that acceleration is gravity, and that is 9.81 meters per second squared. We know Boba Fett starts right here. He launches up into the air. He goes 40 meters off the ground. During this time, so at this location, his velocity is 75 meters per second. 75 meters per second. He continues to go into the air. Here's X initial at 40 meters. Continues to go into the air until he reaches X final. X final is unknown. What is the maximum height reached? That's what we're trying to figure out. X final. That's our unknown for this equation. So let's continue. We have our kinematic equations over here. Which kinematic equation should we use? Okay, hopefully you guessed the third one, the timeless equation, because we do not have time in this equation. So the equation that we want to use is VF squared equals V initial squared plus 2 times the acceleration times delta x, which is just going to be x final minus x initial. All right, so what do we got here? Our final velocity is what? What's our final velocity? What's our velocity right here? 0. That's right. 0. 0 squared is 0. Our initial velocity, starting at our initial position, which is 40 meters off the ground, is 75 meters per second. So 75 squared plus 2 times 9.81. X final is unknown, and X initial is 40. One equation, one unknown. Now, 75 squared, negative 5625 equals 2 times 9.81, negative 19.62 times x final minus, well, actually this gravity is negative 9.81. So that's why we have a negative here, negative 19.62, and negative times the negative 40 will give us a positive, a plus 784.8. All right, so we subtract the 748 over to this side, negative 6409.8. And this will yield a final answer of XF 326.7 meters. And we can go ahead and round that to 327 meters above the ground. That is how far he will launch. If he turns off his jetpack, he's going 75 meters per second. It's going 75 meters per second right here. Turns off the jetpack here. That initial velocity will carry him all the way to there at 327 meters above the ground. Okay, let's step into part 2 of the equation. What is Boba Fett's velocity when he hits the ground if he is dropped from this height? Okay, so we're kind of getting back to the painter situation that we talked about earlier. We got Boba Fett. He's right here. He's this blue dot. He is dropped from that location, and he smacks the ground right here. 327 meters above the ground. Hopefully I will get better at using this sketch pad. But for now it's fine. So what's our X initial? Well, first of all, let's go back up. And I'll ask you guys a question. Which of the 3 kinematic equations should we use? Once again, it will be the 3rd kinematic equation, the timeless equation. So let's write that one down. VF squared equals VI squared plus 2A times delta X. Let's try and figure out what exactly we know and what we don't know. Our V initial, as we know from the last problem, at this location at your maximum height is going to be 0. Your X initial is going to be 327 meters. Alright, down here we got an X final of 0. Our V final is what? It is unknown. That's what we're solving. What's the velocity when he hits the ground? What's our acceleration? As we said earlier, it's going to stay the same. It's 9.81 meters per second squared. Okay, so now we just plug all these variables into our equation and solve the equation. 0 squared equals... Oh, I already screwed up. VF squared equals 0 squared plus 2 times 9.81 times 0. Once again, I didn't put the negative in the gravity. Make sure you're doing that. Okay, don't make that mistake, because then you might get the problem wrong because of a sign error. Gravity is typically negative depending on what orientation you're using. And normally you want to use it as a negative so that everything stays simple. So gravity's negative. And we got 2 times negative 9.81. Let's just rewrite it so that it is easy to see. 2 negative 9.81 times negative 327. All right. VF squared equals 6,415. 6415. So we take the square root of both sides. And our VF, our final velocity, will be 80.1 meters per second. And usually on a test you do want to draw an arrow or something like that just to indicate the direction. Later on we will get into different problems, projectile motion, stuff like that, where we're going to have to even give an angle of the final velocity. This one's a little more simple. It's up and down, straight up and down motion. Therefore our final velocity is directly downward at 80.1 meters per second.